Now, in this problem, we define pk as the kth prime, so p1 is the first prime, p2 is the second prime, and so on and so forth, where k is a positive integer. And this is a number that we construct, say p1 times p2 times pn minus 1 plus 1. We want to show that pn, the nth prime, is always less than or equal to the sum of these n minus the first n minus 1 primes plus 1 for all integers with n greater than or equal to 3. Okay, so how do we prove that? So this is your conclusion. You want to show that, right? So now here's the proof. Here's the proof. And because I do see that you guys define qn minus 1 as this guy, p1 times p2 times pn minus 1 plus 1. So you guys define this guy. You guys define this guy. Okay? And then I do see some of you claim that by a lemma, we do know this is a number, so therefore we must have a prime divisor, right? By lemma 3.1. Lemma 3.1. There exists a prime, and then I see that you guys use q, divides this q n minus 1. I completely agree with you there. Now, here we have to say that this prime q cannot be any one of any q pi's. Pi's where I is greater than 1, less than or equal to n minus 1. In other words, it cannot be p1, it cannot be p2, and cannot be pn minus 1. Cannot be any one of those. If it is, then there's a contradiction. So if not, okay, if not, say suppose q equals pi sum I greater than 1 and less than or equal to n minus 1, then q must divide this p1 times pn minus 1, right? So then this has to be true because it's one of those. It's one of those. And also, q also divides this p1 pn minus 1 plus 1. You combine these two, you will conclude that q divides 1, which is a contradiction. That's in the proof that we have done so several times. So this will be a contradiction. That's why we conclude that q cannot be any of those pi's, because we have gone through this proof in class, and then some of your homework you also use that as well. I suppose that you understand this quite well. So if I have to write it out, then this would be what I write. But otherwise, I can just simply say it because you guys are pretty good, understand this quite well. Now, what can I? In other words, this q, it's none of this p1 to pn minus 1, and it is a prime. Therefore, do you agree that this q has to be greater than or equal to the nth prime? The nth prime. So pn has to, because it's a prime, right? And it cannot be any one from the 1 to pn minus 1. So at least it should be greater than or equal to pn, i.e. this has to be true, right? Also, because q divides q, this guy qn minus 1, which is p, I really don't think that's needed. We really don't need to define that, but anyway, p1 times pn minus 1 plus 1. This means q has to be less than or equal to this guy, right? Okay, this guy, less than or equal to this guy. Now take a look at what we conclude. Q is greater than, which means q is greater than or equal to pn. And then q is also less than or equal to qn minus 1, this guy. Therefore, isn't that what we want to prove? So that's exactly what we want to prove. Pn less than or equal to this guy. Pn less than or equal to this guy. So we finished this proof.